Hello everyone, my name is Nikolina Bodiroga and I'm from Serbia. I come from the University of Novi Sad, Department of Computer Engineering and Computer Communication. The topic we will cover today is evaluation of fleet management, data collection, backend using Cassandra database. Nowadays, the automotive industry is developing rapidly day by day. Modern vehicles already integrate various IoT sensors to provide for better passenger comfort and warn the drivers about safety and functional issues. Also, the emerging self-driving vehicles are equipped with cameras, radars, and LiDAR sensors, which provide information about the vehicle's surroundings. All the sensors incorporate into the vehicle generate data, which can be captured and further processed to enable various consumer and industrial scenarios, such as fleet management, route suggestion, passenger comfort, and entertainment application, etc. As we have already mentioned, more and more vehicles are in use, so there is a greater need for vehicle tracking and resource management. To accommodate the needs of the large-scale industrial and commercial fleets, dedicated fleet management systems are created. As development of the autonomous vehicle progress, new scenarios are also developing. It is expected that the consumer will switch from owning a car to using vehicle sharing system in the future. Such system will allow the consumers to use autonomous vehicle fleet on demand. The request cars will come to the user's address, make the desired ride, and then drive themselves to the garage until the next request. In such a scenario, vehicle position tracking is of great interest in order to ensure the smooth traffic, while the information about vehicle usage can serve as the basis to create different billing options. Additionally, vehicles can use data analytics to collect and analyze current traffic data, weather conditions, and historical road suggestion. This information can be used to predict road congestion in the future and suggest one of the most convenient and time-saving routes to the drivers. Also, the analytics can be used to improve the driving experience. Over the course of the months, the driver's personal characteristics and driving style data can be collected, such as age, weight, and driving speed, typical routes, etc. By analyzing this data, vehicle drivers or owners can interact well with the vehicle through the driving and entertainment information displays, which displays GPS navigation routes, video playback, vehicle safety monitoring data, and so on. According to the results of the data analytics, different driving decisions can be made to avoid potential harmful situation caused by driver stress, fatigue, and tiredness. It is also very important to mention that data coming from the physiological sensor. This data contains information about the current state of the driver, which implies the level of stress the driver is under, heart rate, temperature, pressure, arterial oxygen saturation, and estimation of blood pressure. This information greatly helps to avoid potential accidents. Data acquisitions and storage and fleet management system represent a challenge, primarily due to the large amount of data generated by vehicles, which needs to be stored in real time without data loss. The tools used for data analysis and storage must be extremely reliable, efficient, and secure, but still quite fast. For security and efficiency reasons, data is usually replicated and stored in different clusters. A very important requirement is data security. This can be accomplished by data encryption. Also, the prediction of the cellular network bandwidth is of great interest as a reliable and continuous communication with the cloud of the fleet management system is needed to support different scenarios. In this paper, we will present the architecture of the fleet management system and investigate different options for data collection and storage in such system. The picture of the slide shows the architecture of the data collection and processing system for fleet management purposes. The IoT gateway collects information from all sensors in the car by querying the sensor periodically for their status. Sensors inside the vehicle include GPS sensor, physiological sensor, mass airflow sensor, engine speed sensor, oxygen sensor, fuel temperature sensor, mileage sensor, etc. This data is first processed by different diagnostic applications within the vehicle, and the diagnostic service are integrated with IoT gateway as present in the previous work. Once the sensory data is collected, the IoT gateway forwards it to the cloud server, which causes the controller that accepts the reports. The controller implements the functionalities that support the acceptance of reports coming from cars, their analysis, and entering the database. The stored data can be further processed by the big data system in the cloud, and aggregated data can also be shared with the other vehicle in the fleet. For example, in the fleet of autonomous taxis, the information about vehicle location is of interest for other vehicles in the system in order to achieve the optimal customer service. As already mentioned, each car has sensor that sends to collect data to the IoT gateway. When the IoT gateway collects the data, it sends it to the controller located on the server. The data from IoT gateway it sends to the cloud asynchronously. In the cloud, the data controller is responsible to accept the data sent from IoT gateway in a fleet vehicles, check its format, and verify that the data is generated by the trust source. Then it stores the data in the database. The database controller is written in Python programming language using a web framework. Within the database controller, the functions have implemented for accepting reports for the IoT gateways, validating them, and entering them into database. The accept data format includes vehicle location data, internet connection status, data received from sensors such as vehicle fuel status, mileage, engine status, total vehicle mileage, as well as distance from other nearby vehicle if they are detected. The data stored in the database is periodically analyzed and aggregated. We chose to use Cassandra database because of its scalability, support for high ingest traffic, high availability, and the possibility of grouping and clustering data. Apache Cassandra is a high scalable, high performance distributed database designed to handle a large amount of data across many commodity servers, providing high availability with no single point of failure. It is a type of NoSQL database. NoSQL databases are more convenient for handling a larger amount of data, and that is why they have found a great application in Internet of Things. Also, Cassandra is easily integrated with Spark Analytics engine, which is suitable for both data mining and machine learning algorithms over the collected data. We test the implement data storage and analytics model both in the real world scenario and in the laboratory condition. In the real world scenario, we track the cellular network bandwidth data from the application in the moving vehicle and store it in Cassandra. The data format is depicted in the picture on the slide. It was confirmed that the network bandwidth reports, the data format is depicted in the picture of the slide. It was confirmed that the network bandwidth reports are correctly stored in Cassandra database in a raw format, and that the average ping time over the 4G network was 2.2 milliseconds. The obtained data was then processed on a daily basis to determine hourly or daily bandwidth variance, which can further be used to choose the vehicle route with optimal cellular network coverage or to ensure that quality of service in in-vehicle infotainment application. Load tests were performed in laboratory conditions, and for this purpose, the car movements were simulated with the help of the open source framework Veins. As mentioned above, Cassandra database was chosen because of its compatibility with Spark and support for fast data insertion in the database. To experimentally confirm that the NoSQL database is a better choice for the massive data collection, we compared the performance of Cassandra with the performance of MySQL database. MySQL was chosen as a representative relation database because it is an open source and popular solution, and it stands out by the data insert speed. The data sent from the car to the controller was the same average size for both the database, 1 kilobyte. The Cassandra controller can process and store the reports with interval of 1 milliseconds. On the other hand, MySQL controller could accept reports in a time interval of 200 milliseconds. Therefore, it was confirmed that faster data writing speeds can be obtained if a NoSQL database such as Cassandra is used. The summary conclusion of the entire paper is that the architecture of the fleet management system is presented, and we implement a model for data collection, storage, and analysis in the fleet management cloud. This model consists of the Cassandra database and is implemented by appropriate Cassandra controller responsible for data collection, validation, and database entry. The collected data is processed by Spark. Collecting fleet management data is a prerequisite for the development of new scenarios and consumer characteristics. Information collected can be used in a system that offer cars as a service to end consumers, as well as for various industrial purpose. Thank you for attention.
Thank you, Nikolina, for presenting your paper. Could you please, explain us why, as we can see, you basically collected the information about the quality of the network service. What was the goal of the problem you were basically trying to solve by collecting and analyzing this data?
Yes, thanks for your question. The described method of data collection can be used in several areas. As a very interesting fact, I would like to mention that project I work on, which is data collect from driving. In this way, we use to predict data such as bandwidth, delay on the route along which the vehicle will move. This data is very useful for applications that run inside the car and use the internet, such as television playback application for mobile users, which base its work on the data collected. In this way, it is possible to inform the users on which route the data is more suitable for the operation of the application he uses. For example, it is possible to suggest the users a route on which he will be able to use the application for internet TV, because on the route network, bandwidth is best, for example.